let's try to solve this question over here. An electric stove contains a wire of length 1.1 meter and cross-sectional area of 3.1 millimeter square. So let's try to draw the situation out. Okay, so it's a wire. Let's assume that this wire is cylindrical. What do we know about it? It has a length of 1.1 meter. And cross-sectional area of 3.1 millimeter square. So cross-sectional area is this part over here. The area is 3.1 millimeter square. Of course, we cannot leave this at millimeter square. We have to convert it into SI unit. Okay, so if we like to convert it, we know that we need to eliminate millimeter square. We have to introduce meter square as our replacement. Okay, we know that how should I write it? 1 millimeter is 1 times 10 to the power of negative 3. Okay, because we're replacing the milli over here. We replace the milli over here with times 10 to the power of negative 3. Then, but there's a square over here, means by you have to square the whole thing. So here you need to square, here you need to square. Okay, so if you calculate it, I believe you get 3.1 times 10 to the power of negative 6 meters square. So this is the cross-sectional area of this wire over here. Okay, 3.1 times 7 times, yes, correct. Okay, when the electric stove is switched on, so you switch on means by you are probably directing current through this wire over here, then the wire becomes hot in response to a flowing charge. So now there's charge flowing inside this wire, and as time goes on, the wire will slowly become hotter and hotter. Okay, so that's just how an electric stove works actually. Okay, we're not talking about induction stove, we're talking about those direct contact kind of electric stove. Okay, by heating up the metal, like directly heating up the metal. Okay. The material of the wire has a resistivity of 6.8 times 10 to the power negative 5. Okay, so let's write it down. This is 6.8 times 10 to the power negative 5. And they are labeling it with a naught over here. They are labeling it with naught over here because naught here referring to the reference temperature. So they also give you the reference temperature to be 20 degrees Celsius. Okay, when we are talking about resistance and resistivity, right, there's always two temperature. One will be the reference temperature, another one will be the other temperature. Okay, so it's always a change of resistance, or it's always a change of resistivity from the reference temperature to another temperature. Okay, it has to be that way. If it's from one temperature to another temperature and the reference temperature is not involved, the question technically cannot be solved properly. Okay, there's a bit of problem with those kind of questions. So it usually has to go from 20 degrees Celsius to a new temperature, or it has to go from another temperature to 20 degrees Celsius. The 20 degrees Celsius has to be involved. Okay, because this 20 degrees Celsius is what we call as the reference temperature. Reference temperature is the temperature which they conduct experiment to study resistance and resistivity. Okay, it's a standard temperature that we refer to when we are trying to say what is the resistivity of this material. We usually refer to 20 degrees Celsius when we are taking the measurement. Okay, because we know that resistivity, it changes with temperature. So if I tell you, oh, the resistivity right now is 6.8 times 10 to the power negative 5 ohm meter. If I tell this value, it doesn't really carry any significance because it can be the resistivity at 50 degrees Celsius. It can be resistivity at 0 degrees Celsius. So that value itself doesn't have any meaning if we are not referring to a specific temperature. Okay, so in the electrical world, usually people decide to talk about resistivity or resistance by referring to a certain standard temperature, and that standard temperature is usually 20 degrees Celsius. So we are going to keep according to the global standard and say that the reference temperature is 20 degrees Celsius, and at that particular temperature, that particular standard temperature, our resistivity is 6.8 times 10 to the power negative 5 ohm meter. Okay, and the temperature coefficient of resistance is alpha. Alpha is 2.0 times 10 to the power negative 3 per degree Celsius. Okay, so let's write it down. Alpha is equals to 2.0 times 10 to the power negative 3 per degree Celsius. Okay, determine the resistance of the wire at an operating temperature of 120 degrees Celsius. Okay, so this is the other temperature that I was talking about. Just now I was saying that it has to be two different temperature. One of it has to be 20, right? So the one of it is 20 degrees Celsius, our reference temperature, and the other temperature that we're talking about here is 120 degrees Celsius. Okay, so they are going to operate this wire at 120 degrees Celsius, and they want to know the new resistance once it elevates up to 120 degrees Celsius. Okay, so they're interested with the resistance and they are interested at temperature 120 degrees Celsius. So it will be wise that we use the resistance equation. Okay, the resistance equation and how it relates to temperature. This will be the equation. But we have to be very clear when we are using this equation, in that if we are using this equation, those symbol that comes with a not, right, they have to be referring to the reference temperature, which is 20 degrees Celsius. So this T naught here has to be 20 degrees Celsius. This R naught here will have to be the resistance, or it has to be the resistivity at 20 degrees Celsius. Okay, it has to be that way. Okay, there are certain books that say you can go from 120 degrees Celsius to 220 degrees Celsius. Well, it's just not suitable to do so. Okay, there's a long reason why. Okay, but it's just not suitable. Okay, you have to pack it on a reference temperature, and in the global standard is 20 degrees Celsius. Okay, then you have the symbol that has no knot in it. The symbol without knot in it will be the R or the rho at another temperature. Okay, at the other temperature. Let me write at the other temperature. Okay, I believe you can see that the other temperature for this question over here will be 120 degrees Celsius. Okay, so T here will be referring to the other temperature. Okay, so now I think we can start to do some substitution here. Okay, but I think if you want to substitute, I believe you are given the alpha, you are given the other temperature is 120, you are given T naught, which is 20 degrees Celsius. So what you might have issue to find will be R naught, which is a resistance at reference temperature, and from there you are able to find your R. Okay, this is your target over here. Okay, so we might need to find R naught first, then we have everything we need to find R. So let's find R naught first. Okay, R naught will be just another rho L over A, right? Okay, rho L over A, but we have to be clear, this is the rho at reference temperature. This is not the rho at 120 degrees Celsius. This is the rho at reference temperature, because we are finding the resistance at reference temperature. Okay, so R naught here will be, rho naught here will be 6.8 times 10 to the power negative 5. The length is 1.1, and the cross-sectional area, I believe we have it, it's 3.1 times 10 to the power of negative 6. Okay, so you can calculate this value. Actually, I didn't really calculate it. Sorry, my bad. Why I didn't really calculate it, what I do is I substitute this value right inside here. Okay, because I'm going to replace it with R naught. So here I go, I'm going to directly substitute it here. 1.1, 3.1 times 10 to the power negative 6. So this whole thing here will be R naught. Then 1 plus alpha. Alpha is 2.0 times 10 to the power negative 3. Then T minus T naught. T is 120 degrees Celsius. T naught is 20 degrees Celsius. Okay, so well, I have everything I need. What I need to do is just put it into my calculator, and I believe I will get an answer of 28.95 ohm as the resistance at 120 degrees Celsius. Okay, so it's a pretty straightforward question. Okay, what you need to determine is actually just the R naught actually. Okay, let me write it in the way. R will be equals to R naught 1 plus alpha T minus T naught. Okay, so hope you can see that what am I substituting here for every part. Okay, the R naught can be determined because it comes from knowing the original length, the original area, and the original resistivity at the reference temperature, which is 20 degrees Celsius. Okay, so this question combines our understanding of 4 different factors that affect the resistance of a conductor. It's the length of the conductor, the cross-sectional area of the conductor, the material that we use to make the conductor, and lastly, the temperature of the conductor. All 4 factors are being put into this situation here when we are solving this question. So that's it for this question. Thank you very much.